Hello, and welcome back to Introduction to Algorithms. We are in chapter 2, searching various search problems we have been discussing with the emphasis on the virtues of computer science or paradigms to first carefully specify the problem we want to solve, as well as the primitive operations that we're allowed to use in designing algorithms and the computational cost that is charged to every such primitive operations. For example, is it bit cost or is it unit cost? Unit cost meaning we only count the number of operations and ignore how large the data items are that are processed within using each primitive operations. And you all know the basic search algorithm. So the algorithms are not really new. That's not the purpose of even this introductory course, but instead the focus here is on the general principle and realize the abstractions that are taking place that allow us to obtain a large picture and overall view, as well as to make them explicit, which abstractions and which generalizations we use. So let me recall for your benefit the slides from last time. Here we are. So we already talked about linear search. I'm briefly going to recall that. We talked about neighbor search, which is a refinement. The specification is a refinement from linear search. We talked about binary search and uniqueness, provided that the data is already sorted. And we postpone throughout this chapter the question of how to obtain sorted data, because that's the topic of chapter 3. We've started talking about hashing, and this is where we're really going to take off today. Then we'll talk about median and its generalization, order statistics. I will, of course, specify the problem of median and order statistics. And then we'll talk about geometric search problems such as range searching, range counting first in 1 dimension and then in 2 dimension as usual, with focus on the virtues of computer science. So the general setting is we have a set and we have a finite sequence of elements from that set, among which we're supposed to search for example, some given element y. And on the computer side, imagine this finite sequence is a mathematical object, and computers, this is represented as an array. So you already see this close connection and correspondence between data types in computers and mathematical structures, which we're actually going to explore in further detail in chapter 4. So this is kind of a to get you already warmed up. In chapter 4, we're going to talk about data. What is data really? With topic that is commonly ignored or treated only as a side question in other algorithms courses. We're going to dedicate an entire section to that. So anyway, let's move on. So one variant of the search problem specification is the goal to find an index in the sequence where the given element y occurs, if such an index exists, or an indicator that no, the element does not occur in that sequence. And if several y occurs repeatedly, then any such index is a permitted return value. Okay, so that's a specification, probably capturing and formalizing what you already had in mind, but now making it explicit and formal and unambiguous. For example, if there are several elements having the value y, then we do not require that the first nor the last or any specific, but any index be returned. So yes, primitives that are we can use in algorithm design is access. Yeah, given an index into the array, into the sequence, return the element at that position, and comparison for equality and negated inequality, but not order. That's we're going to consider later, and we're going to charge unit cost. We're going to ignore the size of the data elements in the set X as well as the binary length of the index, which is a first order approximation to predict the performance of this algorithm, but later one may and will refine that, actually, particularly when we talk about sorting algorithms. We consider, for example, radix sort. There, the whole point is about the binary length of the data being processed. Okay, so let's move on and recall linear search. Nothing interesting happening here. Then we talked about neighbor search, which is a refinement, particularly in case with the case that the array already is sorted with respect to some total order. For example, when we're talking about complex numbers, then neighbor search is not even well defined, well specified, because in complex numbers there is no total order. But when we want to search for student IDs, these are integers, these are totally ordered. And thus we allow in the algorithm design an ordered comparison, and we impose the hypothesis that the input data is already sorted, strictly increasing, and particularly that there are no repeated elements. This is a subtle but important hypothesis here for the problem specification to be well specified. Namely, the purpose is to output the unique index. Actually, that's the whole point. The unique index which already exists and is unique of the element xn and its neighbor, therefore neighbor search xn plus 1, such that the interval from xn including to xn plus 1 excluding contains y. And yeah, with this hypothesis, really such an index n exists and is unique, right? Because we don't have repeated elements, exists provided that y is somewhere between the range of the elements. If y is less than the least element x1, or if y is greater than the last element xn, then this is not well defined, and therefore we implicitly add sentinels. X0 is considered to be minus infinity, and xn plus 1 is considered to be plus infinity. Or put differently, it's just any element which is larger than any element in the sequence. So then everything is well specified, and again, the algorithm is kind of trivial. So let me skip over that part in this recap. Then we talked about binary search, right? Binary search here. And in binary search, again, the hypothesis that the input data is sorted, and now we do allow for repeated elements. It doesn't need to be strictly increasingly sorted, but only non-decreasing. And again, you all know binary search. So the interesting part in binary search is not the algorithm, but the analysis, which pertains to two properties. First, the correctness, and second, the running time. And this is a great exercise in formally proving correctness and formally conducting a runtime analysis. For correctness, observe that we maintain the loop invariant, that y is always contained between position L, the element at position L and left, and the element at position R right, with less or equal here and strictly less here. So this is correctness. And this is true initially because we initialize XL to be the left sentinel and XR to be the right sentinel, minus infinity plus infinity. And now please do verify yourself, prove the mathematical induction step that if this hypothesis is true at the beginning of the loop body, then according to this if then else, it is still also true at the end of the loop body. And since this is a loop, if it's true at the first beginning of the loop body and then at the end, it means that it remains true throughout the loop. That's a principle of induction, right? And this is exactly the comparison, the inequality that makes sure that after one iteration of the loop invariant is still true. Now, concerning the runtime analysis, the observation here is another loop invariant, and more precisely, the induction step in the loop invariant, namely that the length of the subinterval under consideration, that is R minus L, right end minus left end, decreases roughly by a factor of 2 in each iteration after one execution of the loop body. The difference distance between the right and left interval end, R prime and L prime, is at most the distance between right and left end divided by 2, rounded up. And please convince yourself that we do need to round up. I mean, this is in general not an integer dividing by 2, so we do need to do some rounding. But please verify, convince yourself that rounding down is not true, is not invariant, is not necessarily valid after one execution of the loop body. Also here we round down, which is yeah. So here we round up and here we round down, and then from that it's easy to conclude that the number of iterations. So since the length of the interval basically grows by a constant factor, a little bit less than 2 because of the rounding, but still that after logarithmic number of loop iterations, the length of the interval has reached a constant 1, and then it doesn't decrease anymore, and also then the loop condition here in the while condition fails, and thus the while loop terminates. So long story short, the while loop is repeated a logarithmic number of times, logarithmic in the length of the interval, which initially consists of the entire interval, and when the loop terminates, then still this loop invariant holds, and therefore we indeed have found an index R, the smallest index, such that Y is less than XR, this right-hand side. Okay, so that was our analysis of binary search correctness and asymptotic cost being logarithmic. And remember our table about asymptotic growth. Logarithmic runtime is extremely efficient. Even the slowest computer making only one operation every 10 seconds with a logarithmic time algorithm can beat the fastest computer, the gigahertz contemporary computer running, for example, exponential time algorithm. Actually, the slowest computer beat every other computer when the input size is sufficiently large, because it runs an asymptotically efficient, namely a logarithmic time algorithm like binary search here. Okay, so running time is log n, and we've proven correctness, and then we've moved on to the uniqueness problem, which is again an interesting variant of the search problem. Namely, this is a decision problem. Input a finite sequence, find out whether all elements in that sequence are distinct, which means true, uniqueness is true, or report false, it's not unique, some element is repeated. we're not required to report which element or which elements is repeated, only indicating that some element is being repeated. So that's a, specification. There are the variants, reasonable variants, like report some repeated element in the second case, or list all repeated elements. All these make sense, but that's the whole point of a problem specification, to remove all such ambiguity. And here we're considering this variant of the problem where only a Boolean indicator is supposed to be returned. And the algorithm we saw is, again, the algorithms here in this course are not really surprising or sophisticated so far, to be fair. It is an introductory course after all. And this algorithm simply compares all pairs of elements, and when it finds some repeated pair, then it returns that there is a repeated pair, and otherwise, if no repeated pair exists, then it returns one. And trying all pairs means two nested loops here. Some little care is taken that the loop indices never agree, such that this condition is met. And the analysis, runtime analysis, is then straightforward because quadratic time, two nested loops. And observe that this is a obvious upper bound. The two nested loops can never make more than n squared, but also this is a tight analysis up to constant factor. These two loops indeed nested result in the loop body being executed a quadratic number of times. So that's our first algorithm for uniqueness, and actually we're going to consider two more algorithms. The second algorithm works only under the additional hypothesis that the original set is equipped with the total order and that the original data is already sorted. Only then does the second algorithm make sense, because the second algorithm, first, we need the total order for this problem specification to make sense mathematically. And secondly, based on this hypothesis, the algorithm can suffice with comparing adjacent elements, right? So if there's some repeated element, then these two repeated elements must be adjacent to each other. So that means the runtime now reduces to a linear time algorithm, right? Under the additional hypothesis that the data has already been sorted. So this is, of course, a question that we address in chapter 3, sorting, but also the question actually arises, do we have to sort the element in order to get subquadratic running time? Let me repeat that, a very important question. So if without the hypothesis that the elements are already sorted, and we will see later that sorting is a costly process, optimal algorithms cost n log n, so more than linear cost, right? So once the elements are sorted, then uniqueness becomes kind of easy, becomes trivial. But can we solve uniqueness without incurring the superlinear running time n log n? That's the question we now want to address with our third algorithm, unique 3. So that's the motivation, an algorithm between better than quadratic, but without the hypothesis that the data is originally sorted. And that's where hashing comes into the play. And for hashing, we impose an additional hypothesis, namely not that the data be sorted, but that the data be integers, right? So here, previously, the hypothesis was that the data is an arbitrary set equipped with the total order. And now we suppose that the data is integers. And mathematically, that's not a big restriction, right? We can kind of enumerate any countable set, for example, the set of all names in lexicographical order, and thus we can assign an integer to any finite set, or even to any countably infinite set mathematically. But doing that computationally is an entirely different question. So computationally, this is a kind of restriction. Well, on the other hand, any data in a computer already is represented as a finite sequence of bits, and a finite sequence of bits can be interpreted as an integer in binary. So for any computer data type, this hypothesis is also met, right? So we say it again, mathematically, this is no loss of generality. The question is about the computational efficiency, and computationally the question is also, this hypothesis is also always met, but again the question is about computational efficiency, because let's suppose, for example, that the data consists in 32-bit integers, then that means capital M is 2 to the 32, right? Which is 4 billion, quite a large number. And if we're talking about 64-bit integers, then M is 2 to the 64. So that's already approaches the number of atoms in the universe. So mathematically, that's not a big hypothesis, but computational complexity, we will see that the magnitude of M will enter in our algorithms cost in two ways. So, but let's first adjust the primitives, right? So now that the data we're operating on is again an integer, that means we have two kinds of integers here, right? We have indices, which are integers, positive integers. Positive, we start with 1. And we have the elements in the array in the sequence, which are now on this slide for the first time also supposed to be integers, integers from this range, so that these integers can, in principle, be used again for indices. Let me say that again. The elements that we're storing and that we're searching among are now integers, and as integers, they can in turn serve as indices to possibly another array. And this is exactly what hashing exploits. And to formalize this, we have to change the specification of the access primitive. Previously, the access primitive would just return an element from the generic set X, and then now it returns an integer, a natural number, which is exactly what I said before, that can now, with the name M, can be used in turn for access into another sequence, another array. So this is kind of iterable access. Okay, let me illustrate that here. So this is our input array, right, from 1 to n with indices. And the third algorithm for the uniqueness problem, we consider towards the hashing algorithm that makes use of the hypothesis that we're operating on integers, uses and creates and initialize another second array whose indices are now precisely the possible values stored in the sequence, that is an array indexed by indices from 0 to m-1. Observe here that this array starts with index 0. The input array starts with index 1, but that's only for convenience. I leave it to you to simply reshift so that both either start at 0 or both start at 1. But this will make the algorithm a little bit more elegant in stating. So, and the hypothesis is that this is initialized with zeros, meaning false. So far, no element has been found to be present, right? Observe that every index here corresponds to a possible element from the set X, and we use this iterable access, and initially the array says that no element has been found at any of these positions. And then this is the second array that the algorithm sets up and initializes, possibly with a separate loop. And these are the kind of the flags which elements the algorithm has so far encountered. And yes, using our iterable access, every element stored in the input array can serve as index into the second array. And the algorithm then walks through the input array, and whenever an entry is found, x of n, then it looks up, it follows the iterable access to check whether an element with that value has already been observed before. Then if so, then it returns 0. There isn't a repeated element. It doesn't know which one, but we're not supposed to return which one. And otherwise, it marks that position as having been observed, as being present. This is the, again, iterable access, now with the assignment marking the flag here that we've seen an element with value x of n, okay, integer. So that the next time, if the next time an element with that value occurs, then the if condition strikes and reports that. So, and if the loop runs up to the end and never detects a repeated element, then the algorithm will return 1. All elements are distinct. So yes, the correctness of this algorithm is obvious, and the analysis is also obvious. So this is a single loop, n iterations. So this is a linear time algorithm, right? Which answers purportedly our initial question: can we solve the uniqueness problem in linear time without the hypothesis that the data has already been sorted? We don't need to sort it here using this algorithm. So this seems like an optimal algorithm. Linear time is obviously optimal because any algorithm for the uniqueness problem obviously must look at every single element if we don't have any other hypothesis on the elements. So end of story. We've designed and analyzed an algorithm and we've proven it optimal. Or is it the end? Now let's look more closely. And this time we're not going to look at the bit cost, which is a different issue by itself. And I want to encourage you to analyze the bit cost right here. In this problem, everything is about integers, right? And so the binary length makes sense not only for the indices, but also for the data being stored. So please, maybe this is a great idea for a quiz, right? So please think about it. What is the bit cost of this algorithm? But here we want to look at another cost, namely the memory cost. How much memory does this algorithm use? The previous two algorithms, Unique 1 and Unique 2, would only store the input array. So that means linear cost, O of n, in terms of memory, right? Capital N, O of n memory. But here the algorithm Unique 3 employs a third array, right? Namely the array present, and that array has length capital M, not capital N, but capital M. So that the overall memory of this algorithm is O of n plus O of m. Yeah, this should be O of n plus O of m. So that now not only the size of the input data matters, but also the size of the temporary storage, the helper array, and that means the parameter m, that, as you recall, can be up to billions or even the number of elements in the universe easily, right? we're storing 64-bit integers, machine integers, then m is 2 to the 64. And so that means the memory consumption will blow up your computer for sure. So yeah, that's again the example that now we want to look more closely about the performance of the algorithm. And in this case, it's not the running time that is a limiting factor, but the memory. And the famous saying says, time is unbounded. So if we have a slow algorithm, then we just may need to wait a little bit longer or much longer. But memory is bounded. So if you have a computer with like 4 or 8 or 32 gigabytes of memory, and if that memory is exceeded, then the algorithm simply won't run at all. And waiting a little bit longer doesn't help, right? So let me say it again. Runtime is unbounded, but memory is bounded, and an algorithm that exceeds the memory of your computer will simply not run, it will simply not terminate at all. Okay, to be fair, modern computers, of course, have some virtual memory by swapping the RAM into the hard disk, but that is roughly 10,000 times slower if you have a magnetic hard disk, or still 100 times slower if you have a SSD hard disk. So this is really arguably the hardest constraint, the memory. So that means we now need to refine our initial question. I mean, the question was not really interesting, asking whether linear running time is feasible for the uniqueness problem without requiring the input data to be sorted. But can we have the running time linear and the memory something like linear or polynomial in the input size? Here, the memory consumption is not necessarily even polynomial in the input size, capital N, because it depends on the magnitude of the data being stored. Okay, so yeah. So that's our refined question, and that leads us to the next algorithm for solving the uniqueness problem by employing hashing method. Okay, and based on our abstract approach, what we now exploit is that we can conduct not only index access on the data being stored, being integers, but we can also do calculations, arithmetic on these values. And this is really where the hypothesis strikes hard, that we're operating on integers, because if the data under consideration is complex numbers or names in lexicographical order, then there's we cannot add names, we cannot multiply names of people, for example. So here, that these are integers really is the key that enables arithmetic. And the general idea is to introduce another helper array much smaller than the one in the previous algorithm, which was the one hurting our memory constraint, and then to kind of get rid of the first helper array, the middle array, and only store the second much smaller array. And the basic idea is if the data that we're operating on, the number of data items, capital N, is the problem is when the number of data items N is much smaller than the possible values of the data, right? So let's suppose we have 64-bit integers, so M is 2 to the 64, but we only have 1 million of them. So 2 to the 64 is much larger than 1 million. And this is where the overhead strikes, right? And we want to make use of that, because in that case, the second helper array is going to be sparse, very sparse, right? Because out of the 2 to the 64 possible entries, which will blow up the memory of our computer, only very few will ever receive a flag that the entry has been seen, being present, right? So most of these entries will remain 0, will remain without mark throughout the computation. Only very few will receive entry 1, so that's a sparse array. And that's the key idea to save memory, maybe to kind of map that large array, or map only those elements that receive entry, mark, map those entry into the smaller array in such a way that there's no collision, right? So let me say that again. This huge helper array will mostly consist of empty entries. Very few of them, namely capital N at most, will receive a mark. And thus the idea to reduce the memory overhead is, the idea is to only store those entries that receive a mark, and to map them into this smaller array in such a way that there's no collision. 2 different marks here shall not be mapped to the same element, because then that means 2 different elements will be occupied here, and then that means the algorithm might think that 2 distinct elements are actually equal when they refer to the same flag here. So that's the idea, that's the approach here. We our new algorithm, our fourth algorithm for the uniqueness problem, under the hypothesis that the data we're operating on are now integers. And oh, here's the subtlety, namely that the integers here are now supposed to start with 1. In the previous slide, we would also allow 0, but here we start from 1 to m-1, which is subtlety, but becomes important in a few minutes. So now our new helper array is only the second one of small size, capital P. And what capital P is, well, I will tell you also in a minute. So this is our second, or much smaller helper array, and the middle helper array is completely going to be purely virtual in the algorithm design, but will not be even declared or stored. And the idea is to map this imaginary large helper array, its cells, onto the much smaller helper array in such a way that there are no collisions. But this is unavoidable, right? We cannot map a large set onto a small set without repetition. That's a pigeonhole principle, right? That's due to double counting, there must be collisions. There must be a lot of collisions, actually. But this is the whole trick of hashing, to reduce the probability of such a collision. So let's look at this algorithm, and this mapping from the large array to the small helper array is called a hash function. Actually, it will be a family of hash functions, and popular choice of such family of hash functions are multiplying by some fixed integer and then taking the remainder with respect to p. Taking the remainder with respect to p, make sure that the result arrives in this range from 0 to p minus 1. That's a point, right? From 0 to p minus 1. That's exactly the results of this remainder. And what is k? Yeah, that's also a subtle but important point. That's just an arbitrary integer, and different choices of k yield different hash functions. So we'll see 2 choices of k and the different hash functions they yield. And the algorithm will first need to fix size of the small second helper array. And for reasons that also I'm going to explain in a few minutes, this is supposed to be a prime number, right? So prime numbers, remember 2, 3, 5, 7, 11, 13, and so on. You know the physicist joke. Physicist joke. Every odd number is a prime number. Okay, let me say it again. Every odd number is a prime number. So let's verify that empirically by experiment. So yeah, 3 odd number is a prime number indeed. 5 odd number is a prime number. 7 odd number is a prime number. 9 odd number. Oh, that's a measurement error, right? So let's ignore that. 11 odd number is a prime number. 13 odd number is a prime number, and that should be enough measurements to confirm the hypothesis that every odd number is a prime number. Anyway, yeah, joke. So much for the joke. So here we require the size parameter of the second helper array to be a prime number, and that will become important in the analysis, because as you may recall from your discrete mathematics course or from algebra, that the integers modulo of prime form a field, and in particular multiplying, that's important, multiplying two integers modulo p that are not zero will again be non-zero, and that's the reason why here we exclude 0, because things start to break down if we have the element 0 here. But since p is a prime, if we start with non-zero elements and we multiply them, for example, with k, then the result will again be non-zero, and so, thus 0 remains available as a special indicator that we have not seen this element. That's why it's initialized with zeros. Let me say that again. 0 serves as the indicator that the element has not been detected yet, like in the previous case. And because we exclude 0 from the data, that means that 0 can be used as this indicator. And the remaining data can be stored here and still leave 0 available as indicator. And multiplying a non-zero element with some other non-zero element modulo a prime number will again be a non-zero element. That's a property of being a prime number. So that's why we suppose this to be a prime number. And the algorithm will take that parameter k that parameterizes the hex function randomly from 1 to p minus 1, again avoiding 0 to avoid the 0 multiplication problem. Okay, that's a initialization phase, and then the algorithm will again walk through the input array, and for each entry in the input array, evaluate the hash function. This is what's happening here, right? And then look at the corresponding position in the small helper array. The large helper array is now entirely skipped over. And if the position in the small helper array indicates that the element has already been seen, then the algorithm will report that it has found a repeated element. Again, it doesn't report where it's been found, only that it has been found. And otherwise, and that's the interesting part, the algorithm proceeds, does not just report that it has not been, the algorithm will mark that element as having been seen. But there's an important point about the collision that I'm going to illustrate on the next slide. So let's proceed to the next slide. And yeah, but first observe again that this previously large helper array is now entirely absent. It's kind of like skipped over by taking directly applying the hash function from the input array into the small helper array, and thus saving a lot of memory. But the question then arises, what is, well, the memory consumption is now very good, right? We only have this small helper array of size P, but what about the running time? There's this inner loop here that I'm going to explain about collision and about the correctness because of that very point about the collision. So what's up with this collision? Let me talk about collisions here. So collision is the following. So here you see the algorithm, and now let's consider an example. Parameter P, the prime parameter is 17, right? 17 is a prime. And let's suppose that the other parameter for parameterizing the hash function K is equal to 1. So that means our hash function is just takes X multiplied by 1. So nothing happens here. And taking the remainder modulo 7, nothing serious here, right? And now let's simulate that algorithm with some input data. Here you see the input array, and let's suppose the first data item is 17. Okay, input array is 17, fair enough, right? And what will the algorithm do? It will look up, it will calculate the hash function. 17 modulo 17 is 0, so it will look up at the position 0 in the small helper array and find that initially that is initialized with 0, meaning it's not equal to the current element, right? So this inequality, this test fails, and the algorithm proceeds to the next. Well, the while condition already fails, and the algorithm will store the currently detected element 17 in that helper array position 0. That's the first element processed, and the while loop here is not even touched. Now the algorithm looks at the next element, 34. Here is 34, right? And the algorithm looks at element 34 and calculates the hash function. 34 modulo 17 is again 0, right? 34 is 2 times 17, so it's again 0. So when processing the next data item 34, the algorithm looks at position P equals 0 again, and this time the 0th position in the helper array has already been occupied. It has received the value 17. So this time the while loop condition does strike, and then so the if condition is executed, and to check whether the value 34, the value in the helper array 17 is equal to the new value 34 that we want to store. It's not. So the if condition is wrong, which means that the algorithm now proceeds to this line, namely looks at the second position, position with index 1. Okay. Now the while loop is executed a second time, looks into this position, finds that the index here is 0, right? The stores, it's already still initialized, untouched, so that the second time the while loop is executed, this condition fails, and it stores the new element into this position. So what you observe here was a collisioning happening, namely 34 was initially supposed to be stored here, but this entry was already occupied with 17, which had the same hash value as the new element 34, and therefore the algorithm proceeds to the next element entry in the helper array and stores the new entry 34 there. What happened here? Okay, moving on, the third element that the algorithm here in this example is processing is minus 17. Minus 17 again has hash value 0, like 17 and like 34. So what the algorithm will do, calculate the hash value 0 again, look at the 0th position in the helper array. It is already occupied, it's non-zero, but it's different from the new entry, it contains 17. The new entry is -17. So it proceeds to the next entry in the helper array and starts over again with the while loop. This next entry in the helper array is already also occupied, but it's also different. It's 34, different from -17. So now the algorithm looks at the third entry in the helper array, and this is finally still free. This is still marked 0. The while loop stops, and the new entry -17 gets stored into this position in the helper array. Okay. Then number 13, number 3 gets presented to the algorithm. Hash value of 3 is 3. This entry is still available. Algorithm stores 3 and is done. Then 20 has the same hash value as 3, so it's stored 1 entry left, and so on. 51 also has same hash entry, so but this is already occupied. This is already occupied, so this is where the entry arises. Okay, so this was the first example that illustrates how the algorithm deals with collision when there's no repeated element. The problem is, of course, what if the array gets full? And also the question is, how often does the while loop here get iterated, right? So if we keep on feeding to the algorithms multiples of 17, then these multiples of 17 all have the hash value 0. And thus each time the algorithm will start at this element, find it occupied at this, find it occupied, and then it will even look at this, although this has a different hash value, but it already has been occupied, and the algorithm will run through the entire helper array, so that this inner loop could be executed up to p times, right? So that the running time analysis could be n linear, but times p, the prime number parameter. That's one problem. Furthermore, what if the array gets filled? So in this case, the algorithm will eventually not even find a free position at all. So that means in this case, to avoid this case, the p, the parameter of the second array, should be at least as large as n, the parameter in the first array, which means that the running time n times p is, in the worst case, again, quadratic. So we're back to square one. This is a quadratic time algorithm, but it's in the worst case, it's quadratic. And intuitively, if we choose p larger, maybe 100 times n, then it should be very unlikely that the algorithm needs to walk far in the helper array. And there's a rigorous analysis of this. What if we choose p sufficiently large and k at random and have random input data? Then there's only a small probability that the algorithm will have to execute this while loop more than a constant time. And refinement of that is to have a two-stage hashing, namely to have additional hash arrays attached to each position here. But that's far beyond the purpose of this introductory course. So let's conclude our discussion of hashing with a second example of collisions. Namely, here we have again the value 17, 34, and -17 stored, all share the same hash value, but stored in linear collision handling. And here's another choice of values, like 6 has hash value 6, -11 also has hash value 6, so it starts here and then proceeds here. 23 has also hash value 6, so it starts here and proceeds here. 40 has hash value 6 and starts here, and so on. So that concludes our discussion. So that the memory consumption is now O of P, and the running time is, in the worst case, N times P, but P should be larger. But on the other hand, hopefully not much larger than N, so that in the worst case, this is a quadratic time algorithm, but in practice, it is this is a rare case. And this leads us to the question of average case analysis of algorithms as opposed to worst case. So this was a worst case analysis, but this is usually an overestimation and average case analysis. And then there's amortized case analysis, and then there's a competitive analysis, and there's online analysis. There are so many ways, different ways of analyzing algorithm beyond the mere worst case running time that we're focusing on in this introduction course. So this is kind of cross promotion to CS500 design and analysis of advanced algorithms. So please stay tuned and subscribe to this advanced course at a later point. So yeah, that concludes our discussion of hashing. We've seen 4 algorithms actually for the uniqueness problem. The first had quadratic running time, trivial algorithm. Second had linear running time, but required the data to be sorted with respect to total order. The third algorithm would again have linear running time, but required the data to consist in integers, small integers, because that would otherwise the memory would blow up. And finally, our hashing algorithm here that achieves worst case quadratic, but average case linear running time and linear memory. But the analysis of that, randomized analysis, expected case analysis, requires advanced number theory and goes beyond the purpose of this introductory lecture. Thank you. So to wrap things up, right. So what we're going to look at next time is order statistics. So let me wrap up by specifying the problem of order statistics. Right, order statistics is a generalization of median. So what is median about? So the median is kind of an element which has half the elements smaller and half the elements larger. So here you see an illustration, and in particular, the difference between median and mean. In a symmetric distribution, median is the same as mean. There's a third element, which is mode, that I'm going to mention in a minute. So here, median is equal to mean. But here in this example, the median is larger than the mean. Mean is kind of the average, right? So, and in average, that means that small elements contribute less than large elements. So that means the mean is here, whereas median means that half of the elements are on the left side and half of the elements are on the right side if the data were sorted. But of course, we're treating here the case that the data is not sorted. Well, later we're going to treat that case. So that's the median. And in this case, this is a skewed distribution. In the case of this skewed distribution, the median is actually less than the mean. But again, the point here is that half the elements are smaller than the median and half the elements are larger. So let me again emphasize the difference. So if we have one extremely large element, right? Let's say 1 million, then that element will affect the mean, right? It has a large weight in the averaging sum, right? But it affects the median only by at most 1, because it only adds one element to the to those that are larger than median. So median kind of only counts how many elements are smaller and larger than the median element. Mean also takes into account the value of the elements. And if the value is very large, then that affects the mean a lot and the median only a little bit. That's why the median is sometimes considered a little more robust. And same here. And mode, we're not going to talk about mode, but let me also clarify that. Difference mode is the largest element, element that occurs most frequently. We say it again, an element that occurs most frequently is a mode. So here, mode. So yeah, calculating the mean, the average is easy, right? So you just take the weighted sum of the elements. That's a linear time algorithm. The median calculating is a little bit more difficult. It's maybe much more difficult if the data is not sorted, right? So, and then there's a generalization of the median. That's the order statistics. So median is kind of the half order statistics. The n over 2 order statistics mean that n over 2 elements are smaller and n over 2 elements are larger. The kth order statistics means that kth element are smaller and n minus k elements are larger. Let me say that again. Kth order statistics means that k elements are smaller and n minus k, the remaining elements, are larger. And depending on k, that recovers the median, right, when k is equal to n over 2, but it also generalizes that and provides more information. And that allows us finally to specify the median and more generally the order statistics problem. Input is such a finite sequence of elements equipped with the total order so that we can even speak about being smaller or larger. And this parameter k, and the goal is to output the median, or more precisely the kth order statistics, that is an element, or rather the index of an element, which has k elements less than the element and n minus k elements right. Or more precisely, because it might not be precisely k elements, satisfy this inequality. So that's the specification of the median and more generally the order statistics problem. And we're going to discuss algorithms for that problem in the next slide, in the next session, with primitives allowing for array access, indirect access, and for ordered comparison, less or equal, both at cost 1. So that's all for today. And as usual, I'm going to stay online a little bit longer and answer your questions. So for now, thank you very much for your attention. And yeah, let's stop here.